In this example problem, we have a charged ball of hair resting on a Van de Graaff generator. When the generator is turned on, it builds up an electric field. In this case, it must be a negative source. That generator must be collecting electrons on it because it's going to repel this negatively charged ball of hair that itself has too many electrons. And it repels in such a way that this hair is going to accelerate vertically. And the problem asks for, well, what is the mass of the ball of hair? So we're dealing with some forces. We have a charge, we have a field strength that applies forces to charged objects. We have an acceleration. So hopefully you're thinking, hey, Newton's laws, right? F equals ma. And we should be thinking about a free body diagram. So I'm going to draw my tuft of hair with some mass that I don't know. And usually the first thing to draw on there, they say vertically, they give you a hint that gravity must be in play. And so I'm going to draw the force of gravity on here. What I do know, though, when I draw these arrows is that we have an acceleration, and it's accelerating vertically. And so, again, not on my free body diagram, but off to the side, I might indicate that my acceleration is up, which suggests that my net force, when I add them all up, should also be upwards. So that kind of informs my decision on the arrows. And so this other force, well, that must be that electric or electrostatic force. So I'm going to draw a big arrow up and label that Fe. So those are my two forces. And ultimately, I'm going to set up and say, well, the sum of those forces has to cause that mass to accelerate. And those two vector forces are my electrostatic force and my weight, or Fg. And when I add up, they equal m times a. So that effectively is going to be the equation, but we've got to dig a little bit deeper here. What else is given in this problem? So like most problems, we're going to identify what we know in this problem. Well, we know what A is. A is upward at 4.2 meters per second squared. We'll assume up is the positive direction. They tell us this 42 microcoulomb. Well, that is a Q, a charge of negative 42 microcoulomb. Now, anytime we're going to use charge, we always want to be in units of coulomb. And if you recall, micro is 10 to the negative 6. So right here, I can set up my fence posts, and I can convert from microcoulomb, sorry for my one note here, microcoulomb to coulomb. And 1 microcoulomb is the same as 10 to the negative 6 coulombs. In fact, that little mu, that little u variable, is literally 10 to the negative 6. So an easy conversion is to take 42 microcoulombs and say 42 times 10 to the negative 6 coulombs. You literally can substitute 10 to the negative 6 in for mu, and you're in coulombs. And so without doing anything here, I know, well, that cancels, I'm in coulombs. I'm going to have 42 times 10 to the negative 6 coulombs, and I can plug it in my calculator just like that. Even though that's not traditional scientific notation, it would be 4.2 times 10 to the negative 5th, but that's just a number, right? It's 42 basically divided by a million, and we can calculate with that. Right, so let's look at what else we're given. We're given this 840 newtons per coulomb. Well, that's a field strength, and we use big E for that field strength, and that's 840 newtons per coulomb. And then what else do we need? Well, we need Fe, we don't know. Fg, we don't know. And we don't know our mass, right? So these are all those things in those equations. And hopefully we can identify some of these things. Well, we know that to find an electrostatic force, that is going to be charge times field strength. And so I can calculate Fe directly. I know that that arrow is going to be pointing upwards, so it's some positive value. When you deal with charge, these negatives can be a little bit tricky. They are just they're not a direction like they might be with what we've done prior in this year. They're really just an indication of whether it's going to attract or repel. So once I know that it's repelling, the negative isn't really useful. So I'm just going to use the magnitude of the charge, which is 42 times 10 to the negative 6 coulombs, and I'm going to multiply that times the strength of the field, 840 newtons per coulomb. And notice if I put the units in there, that coulombs cancels with coulombs, I can get newtons, which is exactly what I want for a unit of force. And so my electrostatic force, I'm going to create a little bit of space here. my FE is going to be, and I'll pull my calculator out, I'm going to type in 42, that times 10 to the negative 6, we use that EE, that second in the comma, gives a little capital E, and all I have to do is put the negative 6 there, and then I'm going to multiply that by 840, and I should get a value of 0.03528. It's a small amount of force. It's an upward value of 0.03528. When you're using these numbers, I would recommend staying to 3 significant digits, so I might round it to 0.0353, but at this point, 1 extra digit is no big deal, and I might use that in my calculator and even store it there. Now, what is FG? Well, they haven't told us the mass, but if I knew the mass, I would take the mass and multiply it by 9.8, right? The acceleration due to gravity, assuming we're on Earth here. So when you lay everything out, we can now substitute some things back into this equation. So I'm going to head back over here, and I'm going to plug in what I have. I have my electrostatic forces upward at 0.03528 newtons, plus Fg. Well, Fg is actually downward, right? It's a negative arrow. And so I'm going to put in here negative, and it's m times 9.8. M times 9.8. And notice that negative really comes from that 9.8 being negative. And then on the right side, I have m times my acceleration up here of 4.2. And if you notice, now I have one equation with only one unknown variable, m. And I can isolate that. So I'm going to do a little bit of algebra right here. I'm going to add that m times 9.8 to both sides. And notice those are like terms. I have m times 9.8 and m times 4.2. And so what I have left here on the left side of my equation is 0.03528 is equal to, and now I'm adding 9.8 and 4.2. A little mental math here, but I'll double check my work. 9.8 plus 4.2. Hopefully we can come up with that nice round number of, really I have m times 14. And if I want to solve for m, my next step then is to just divide both sides by 14. All right, so it's going to make that, take that force and divide by 14, and I'm left with an amount of mass. So I'm going to take 0.03528 and divide by 14. And I'm left with 0.00252. 0.00252. And what units would those be? Well, that's mass. And the standard unit for mass, we use meters, kilograms, and seconds in physics for standard units. So this is going to spit out in kilograms as long as I've used meters per second squared, newtons, coulombs, any of these standard units. Now, it's probably a small amount of mass to be described in kilograms, so maybe we do a little conversion. Let's write this in terms of grams, right? And so I know that if I want to get rid of kilograms and go to grams, there are 10 to the positive 3 grams in 1 kilogram, right? There are 1,000 grams in a kilogram. So really I'm just multiplying by 1,000, and I get 2.52 grams as the mass of this ball of hair, which seems reasonable for a little tuft of hair. Might be a little too heavy, but this is going to work for us.